Sarah Ballard be our colloquium speaker today. Sarah received her PhD from Harvard University in 2012 and moved as a NASA Carl Sagan Fellow to the University of Washington in Seattle. And we're very happy that she's here today, that she's allowed to speak today, because even though it's the NASA Carl Sagan Fellowship, she's not a NASA Encoded.
Yeah.
Sarah works on detecting exoplanets, so planets in solar system outside our own, using novel techniques, as well as characterizing those exosolar planets. And she's found hidden planets, as well as worked on novel techniques for detecting them in the Spitzer Telescope, which is an infrared space telescope. She has received awards for her work, including the Richard Doxey Prize by the AAS. And today, she will tell us about asteroseismology and exosolar planets, two very rich fields in astrophysics, in one talk. So go ahead. And before I forget, and I will shut the door, for some reason, if you have not checked your email in the last week, you might not know that she's also giving a public talk tomorrow at 4 p.m. At the Genomics Auditorium. That's correct?
Yeah, the Center for Systems Biology or whatever.
Exactly. So that's a few blocks over. And we'll be going there, a group of us will be going there, and it's at 4 p.m. and at 5 p.m. there will also be a nice reception.
Should we bring kids?
Sure. Yeah. If it's a public talk, no?
Yeah. Oh, of course. You're asking me. Oh. Yes. Oh, yes, of course. Oh, okay. So for the general public, I always try to put in a lot of multimedia. There's some classical music. There's some reading from poetry. So these are things that middle schoolers and up can appreciate, but young ones, maybe there's moving pictures. I don't know. Yeah.
So you're bringing your grandkids and your grandparents.
Yeah. Right. Oh, yeah. It's definitely meant for grandparents. So. Thank you, Mariam, for that wonderful introduction. So I understand that this microphone isn't actually broadcasting my voice; it's just on the video. So how loud do I have to speak to be heard in the back? Okay. So the title of my talk is Exoplanet Validation by Asteroseismology, and I picked this particular image to begin the talk because it evokes a lot of the themes that I'll be touching on. So this is actually a press image that was generated for a different planet that was discovered by the same NASA mission that discovered the planet, which I'll be describing in detail in this talk. But it's so evocative. So you can see this terrestrial planet looming in the foreground, roasted by the insolation of a sun-like star. And then in the background, also suggested within this diagram of the star are paths of different seismic waves, and a study of sound waves within this star underpin our understanding of its physical nature, its physical extent, and its mass. And the reason why this is so interesting is something I'll explain in this talk, how it applies to exoplanets. So as a brief outline for my talk, I first want to contextualize the study of exoplanets generally, especially the study of exoplanets right now. And what's interesting about exoplanets, especially since 2009, is how dissimilar the vast majority of exoplanets are from anything we can study in the solar system. So it sort of used to be the case that people would ask whether or not systems of planets around other stars looked anything like that around our own sun, and astronomers would hedge and say, of course, we don't have the techniques yet to identify planets around sun-like stars, they're very hard to find, and so forth. Now we actually know that we are very different. The Earth and the other planets around the sun are very different than other planetary systems around stars simply because of the type of star we orbit. That's unusual. And for another reason I'll be touching on in this talk, which is that we have no planets in this intermediate range between the Earth and Jovian planets, which are actually the most populous type of planet in the universe. This is one such planet. And the reason why I call it a laboratory, this is only a metaphor, it's only partly metaphorical. So these planets don't exist in the solar system and can't be studied, and so exoplanets kind of comprise this interesting laboratory for a lot of different physics, and I'll be touching on the different types of physics involved. But the reason I say it's only partly metaphorical is because a lot of this work is now actually underpinned by work being done in labs, which is something that I'll refer to and how we know partially about the composition of the planet I'll be describing in detail. So with that sort of setup, I want to put the planet KOI 69 under a microscope. Now this nomenclature, KOI, stands for Kepler Object of Interest. In a Yeah, I did a press release, as Mariam was saying, for the hidden planet. The angle actually was for the invisible planet a few years ago, and the person who wrote it up in Time magazine, Mike Lemnick, said it's very familiar, to the police, referring to a person of interest. And Kepler object of interest, indeed, hasn't been confirmed as a as a convict or anything yet. This is just an object which is designated an interesting probable exoplanet, and it's now a full exoplanet for reasons I'll kind of explain, but it still has this designation, at least for now. And this is a system for which the physics is very rich, from sound waves in the star to photometry to gravitational perturbations. And for this particular system, folding together pieces of this analysis enabled us to constrain different properties of the planet. In particular, one property is constrained for KOI 69 better than any planet outside of the solar system. And that has some historical context that I'll touch on. And I'll close with a discussion about how studies of this planet at multiple wavelengths fortuitously allowed us a piece of understanding about exoplanet study in the post-Kepler era. So if you haven't heard, even though the Kepler mission was launched to fly for 4 years, and even though it was granted an extended mission, the mission is now hobbled and over. And so I'll touch on what we have still in hand to study exoplanets and how KOI 69 helped us understand the resources that we had. So I'll start sort of with the exoplanet as laboratory, but it's important to begin with how exoplanets are really detected. And the method that I'll be touching on for the vast majority of this talk is the method that's nearest and dearest to my heart. It has to do with the transit method. At this point, usually in talks about transits, there's a cartoon diagram of a planet passing in front of a star, and as it does so, it blocks some of the star's light. In this particular case, I thought it was apt and appropriate to show a real transit. So this is a sun-like star, as sun-like as they get, and being observed by NASA's Solar Dynamics Observatory. And in front of this star passes the planet Venus. So this image, in addition to being a stunning movie, it's scientifically very rich because of the number of time scales you're observing in this picture. So you can see the transit of Venus passing in front of the star takes about 10 hours. In contrast, the star itself, our own sun, is a very dynamic object. You can see that it's rotating slightly even over that 10-hour period. The sun rotates with a period of about 30 hours. You can see this magnetic activity manifested in these coronal loops. What I really want to draw your attention to is sort of the roiling surface of this star.
Are you sure the sun rotates at 30 hours?
Sorry, 30 days. Yeah, I'm not sure that it rotates at 30 hours. I'm very unsure about that.
This was the UV image. That doesn't look optical.
Yes, it's like 170 nanometers or something. Yeah. And so this star, like the star KOI 69 around which orbits the planet that I'll be describing, has an outer convective region. These individual convective cells, each of which are about the size of the United States, rises and falls with a time scale of about 5 minutes. So as this convective cell rises, it reaches the surface and falls, and it does this with a characteristic time scale which is so close to the sound speed of the star that it excites these standing acoustical waves. And these standing waves, much like the study of seismic waves of our own Earth, are a probe of something which would be otherwise completely unstudyable. The surface of a star beyond that is literally impossible to see, optical depth greater than 1. And this is one way that we got at the inside of the star, knowing its age to plus or minus 1 billion years, which is a comparable timescale, as you know, for the Earth related to habitability and so forth. So here's the actual brightness measurement as we see. So I promised a video of a cartoon. So you can see as the planet is passing in front of the star, unlike with our own sun, for which we can resolve the planet and the star distinct from one another, with transit observations of other stars, this is not possible. What we observe is the brightness of the star changing as a function of time, and the amount that the star appears dimmer, that decrement, corresponds to the fractional amount of light that the planet blocks in front of the star. And so this brings me to the crucial point. We only know the planet as well as we know the star, which is another reason why asteroseismology was so crucial for our understanding. And it all begins with the Kepler mission. So the reason why transiting planets really skyrocketed to sort of the most fruitful method of finding planets was because of the singular mission launched in 2009. So I'm showing here the Kepler footprint broadcast against the northern sky. This was a NASA mission of discovery, staring at a single patch of sky. It's about the size of your outstretched hand projected on the sky, 150,000 stars. And it's observing these stars with a single silicon eye comprised of about 42 chips plus or minus 1 after the mission started flying. So the question is, when Kepler was launched, it was unclear how many stars had planets. It appeared at the time that the lower limit was 1 in 100, because this was the number of stars that hosted a Jupiter-sized planet very close into the star, because this is where we were able to detect planets from the ground. So as of January in 2013, we've shown the location of all of the planets that Kepler's discovered. Dennis Overby of the New York Times referred to this as the Skittles diagram, the Kepler Skittles plot. So this is showing information not only about the occurrence rates of planets, they're actually very common. This is not 1 in 100 stars that we looked at, especially given the transit probability. But I want to draw your attention too to the fractional number of planets which are of different sizes. So you can see a smattering of giant planets, Jovian-sized planets, but these are not the norm, actually. The norm is planets that are much smaller, and once you take into account
diameters.
Diameters, yes, not masses. So once you
the ones that you've seen, not actually.
Say again.
That's very profound.
You're showing the map you show.
Oh yes, it's only the ones for which the transit geometry is such that the planet passes in front of the star. So for every hot Jupiter planet, it has a 10% probability of transiting. So you have to look at 10 to see 1. Okay.
The intrinsic rate might be much, much more.
Yes, so the intrinsic rate is much higher, and I'll visit it in this slide. What's that?
The distribution could be different as a function of, say, size.
It could be. So our uncertainty also increases. So you have to sort of account for these things. But if you see, if you look at enough stars, it's no longer small number statistics. If you see 100 stars, if you see 1 planet transit and you've only looked at 10, then you're pretty sure it's 1 in 100. But if you see 100 and you've looked at 1,000, then you're pretty sure it's 1 in 10. So this is the occurrence rates of planets that have been uncovered by the Kepler mission. Now this is the number of planets per star with orbits interior basically to that of Mercury. So this is again just a lower limit on planet occurrence rates. And what I want to draw your attention to is this left-hand side of the diagram. Planets are very common. This is a function of the radius of the planet. So
this is taking into account the probability of the orbital plane?
Yes.
Right?
Yes. Yeah, this is folding into account the probability of that orbital plane. Mm-hmm. So we know now that based on the sample that's been gathered by Kepler, 16% of sun-like stars have an Earth-sized planet with interior to Mercury. So we know now too that planets often form in multiple systems. The true Earth analog, there's only one really been identified. It was Kepler 62. But as far as the sort of very suggestive statistic of the number of sun-like stars that have planets, it's very interesting. A large handful of sun-like stars have a planet, but what I think is more interesting is that half of stars have at least 1 planet. Well, how can that be so? Because the vast majority of stars are not like the sun. They're much smaller than the sun. So that's one piece of information we have about planet occurrence and how it's very unusual in our solar system. Most planets don't occur around stars that are anything like our own sun. They occur around much smaller stars. And another thing I want to highlight is that Earth-sized planets are not the most common planets. They're equally as common as this group of planets for which there's just nothing in the solar system to study. These are things between the size of the Earth and the size of Neptune. So in our own solar system, the architecture, we have a few hunks of rock, and then the asteroid belt, and then Jovian planets. And there's nothing in between. And this is something which is very strange given their enormous numbers in the universe. So that alone also renders our solar system a little bit strange. So what I'm showing here is what? I thought I heard a question. So what I'm showing here is a theoretical mass-radius relation for exoplanets, and this is right now populated, in the figure I'm showing, populated by 2 planets, the Earth and Venus. They seem to lie very close to the line of rock, and there's some theoretical understanding of where planets should and shouldn't lie. Below that yellow line is a planet that would be denser than 100% iron. Even getting a planet that's 100% iron is very unlikely, given the collisional stripping rates of planets and so on. And anything lying above that red line is less dense than pure water. So you probably have some fluffy envelope on top of a rocky surface. And I just want to highlight the fact that this entire part of parameter space is unstudied. We basically need exoplanets to comprise an entire laboratory of this part of space. And so each precious planet in this radius range, and given that exoplanets are very difficult to study, you know, the amount of resources required to identify and measure the mass of even a single planet in this range is so great. There's more than 3,000 planets identified by the Kepler mission, and not anywhere near 3,000 individuals who are prepared to identify them. You know, each planet requires sort of cutting-edge resources to make use of these planets as meaningful laboratories. And so I'll just draw your attention to some of the missing physics. So equations of state. So these are enormous solid planets which are exerting pressures on their central cores that we have never measured. So and only in laboratory experiment, for example, have we identified the form that magnesium silicate takes under extremely high pressure, greater than 120 gigapascals, called post-perovskite. You know, and this is probably something that comprises the cores of many of these solid planets. It's not even so the physics is very interesting, the physics of compressing these materials, but also sort of like what are the, I mean, I'll get into sort of the implications for habitability. There's also the inference of composition. You know, depending on what these planets are made of tells us a lot about the formation of planets from the initial circumstellar disk. And then questions of habitability hinge not only on sort of whether or not the planet has a huge gaseous envelope. So based on our understanding of life, we have our own very nourishing atmosphere surrounding us, which enables us to stand up straight. You know, we don't reside under this crushing, heavy envelope of hydrogen and helium. So around these planets, which are between 2 and 4 times the radius of the Earth, do they have huge gaseous atmospheres? You know, or do they have a rocky surface? And this is something which is which needs to be studied. Not only that, not only for the accumulation of heavy atmospheres, but also because plate tectonics are so crucial to life on Earth. You know, are plate tectonics enabled around planets of this nature? Okay, so now that I've sort of posed the question of exoplanets as laboratory, I want to draw your attention to this very particular planet. So the reason I got so interested in this planet is because it comprises such an interesting laboratory. And the way that I sort of enabled that research is to study its radius better than anything that had ever been measured before, so that our uncertainty about the planet is almost entirely due to its mass. And that's enabled by an asteroseismic detection of the star. So what I'm showing here is the transit light curve of the planet. So this is basically the riches that have been dumped in our lap by the Kepler mission. This is 233 transits of this planet, which orbits around its star every 4.5 days, hence the heavily roasted terrestrial image looming in the foreground of the image that I began the talk with. And I just want to draw your attention to the y-axis here. So basically we know that every time the planet passes in front of the star, 218 out of every million photons don't make it to the silicon eye of Kepler. You know, 218 out of every million. You know, this is a number we've measured plus or minus 1.6 photons. I know I'm not supposed to say 0.6 photons, but you know, I mean, it's an incredibly precise measurement, and this is a very, very small exoplanet. You know, so this corresponds to, this is to scale in this diagram here.
With respect to the star that it orbits.
With respect to the star that it orbits, which is about a solar type star. But the exquisiteness of this photometry is sort of due to the fact not only that it was observed with Kepler, it's one of the brightest stars in the Kepler field, it's also the cadence with which we observed the star. So most of the Kepler stars are observed with a cadence of 30 minutes. This particular star was hammered on for 30 months with a cadence of 1 minute. Well, why should that be so? The answer has to do with the acoustic size scales of sound waves within our own sun. Why is there no flat bottom? Oh, the answer is because of limb darkening. Yeah.
So is it like
so we know, I'll sort of show you, it transits at a chord which is about 20% of full stellar radius. Yeah, so because of stellar limb darkening, which is to say the star is not just a perfectly opaque disk, when it's transiting at the limb of the star, it's blocking less light than when it's transiting the center of the star, where the star actually appears to be brighter, which gives it this curved shape.
So stars actually look dimmer near the edge?
Yeah, the effect is called limb darkening. Yeah, it has to do with the fact that the star is cooler. So when you look at the edges, you're actually looking through less material to get to the surface from which the photons are free streaming. Anyway, yeah. Or you're looking through less. So when you take this photometry of the star spanning 30 months and you remove the transits from the star and just take a power spectrum, these peaks appear. I want to draw your attention to the frequency. This is about 1/5 minutes. So you have this comb of frequencies. Something is happening within this star where it's pulsing with a periodic frequency about every 5 minutes. So when I was talking with a visiting professor at Harvard from MIT about this, he said it's just like quantum mechanics. It's just like quantum mechanics. You know, and me trying to understand asteroseismology, it was difficult to understand at first what he meant. The answer is the eigenstates of a pulsating star are also the spherical harmonics. You know, so you have this enormous ball of gas. You make a lot of assumptions based on basic equations in hydrodynamics, and you come up with this understanding for the frequencies of a pulsating hot ball of gas. And it's basically defined by these two quantities. So just as with the spherical harmonics that define the eigenstates of a hydrogen atom, you have your radial mode number and your angular mode number, L. So I just want to draw your attention to the fact that this dominant term, so this first term is about 10 times larger than the second term. You know, I want to walk you through how I understand asteroseismic diagrams and why it tells us something about the star. This dominant term is basically 1 over the dynamic time scale of the star, and it scales just like any kind of dynamical time scale in a body of gas. It's basically the gene's collapse time. You know, how long does it take a sound wave to propagate from one end to the other? This tells us bulk properties about the density of the star. Yeah.
When you look at the star and you see this power spectrum,
yeah.
What property are you looking at?
What property are we looking at?
Looking at the brightness of the star?
Oh, yes. Oh, yes. So what you're seeing, so yeah, so on our own sun, you can actually take Doppler imaging of the sun and see that certain parts of it are moving towards you and moving away from you. On our sun. But because stars can't be resolved, what you actually see is the distortion of the star. So the temperature is not changing very much, but the radius is. So the radius is changing, the brightness of the star is changing by parts per million on a characteristic timescale. So about every 5 minutes or so, the star is looking bigger or smaller and so on. Okay, yeah, sorry, I missed that. It's actually moving toward or away from us at like 15 centimeters a second. It would be very hard to resolve in another star, you know, and that's different across the face of the star depending on which angular part you're looking at. So you can tell bulk properties from the so-called large separation. So you can see if you take modes of the same angular frequency and a different radial mode, then these other terms drop out and you get this property related to the bulk density of the star, just miraculously. This drops out. And the second part of the term ends up scaling as the sound speed gradient within the star. This is how astroseismologists say things about the evolutionary state of the star because they're intimately probing what fraction of the star's core has been converted from hydrogen to helium. In this particular star, we can say based on the so-called small separation, which appears here. And you can see that these dominant terms, which are a factor of 10 larger, the terms in the front drop out when you subtract modes, just based on the magic of physics, drop out when you have modes removed in radial mode space by 1, so 1 up in overtone, and then 2 removed in angular frequency. You just get this term which is very sensitive to the inner sound speed gradient of the star. So that's how we know that about 35% of the hydrogen, which was originally in the core of the star, has been converted to helium.
What depth is it actually probing? If there's some inference about further depth, but the region, what fraction of the radius of the star is actually affecting the problem?
So do you mean like where are the modes being reflected?
Well, when you say when it's a gradient.
Oh.
Getting a gradient, but is one actually getting the gradient averaged over a large fraction of the radius, or is it a gradient in reaching the surface?
So these terms are actually related. It's the integral of the sound speed from 0 to r. So like actually from the center of the star to the surface of the star. Yeah, so it's very sensitive to the gradient of the sound speed at the core. Yeah, okay. These numbers are corresponding to the angular number L. So the mode numbers here are ranging from, I forget, 15 to 20, as the number of nodes of the radial mode actually inside the star. But it's very difficult to detect angular numbers higher than 2 because you can imagine this like bulging piece of gas inside your mind. It's getting too complex to really measure in an unresolved object. Although modes on the sun have angular modes, hundreds have been measured. So based on this understanding of the star, asteroseismologists, based on the small frequency and the large frequency, so the bulk density of the star and the sound speed of the gradient, they build up what they call the intrinsic diagram of astroseismologists, where if you take these two properties, you can basically nail the mass of the star, the radius of the star, and its age. So we know that this star, we know it better than I think I will ever know the measure of my own life. It's halfway through its life, 6 gigayears plus or minus a gigayear. It's going to live 12.6 gigayears before it dies. And I don't even know my own extent to better than 1%. And with this star, I certainly don't know my banking account to better than 1%. And it's, we know this star to plus or minus 1%.
Perhaps you mentioned it, and I missed it. What type was star type?
Oh, I don't think I mentioned the type of the star. I said it was sun-like. The answer is it's actually slightly smaller than the sun. The reason why this matters is because it's one of the smallest mass stars ever, for which astroseismic modes have ever been detected. It gets increasingly hard to measure astroseismic modes around smaller stars because as the surface gravity increases, it prevents the material at the surface from oscillating. So it's like 0.9 times the mass of the sun.
So it's a K?
It's not a K, it's like a late G. Yeah.
This is Kepler data.
This is Kepler data.
So were there any attempts to sort of like most? I mean, so there are other
Oh, yeah.
telescopes that are designed to do asteroseismology.
Yes, they've done astroseismology, but not on sun-like stars. Yes.
Red giants.
Yeah, red giants, yes, for which, meters per second. I was working this out with a graduate student earlier today. Meters per second is the amount that the star is moving. So it's not, and with red giant stars, that a single astroseismic mode can last for days. With Kepler, it's 5 minutes. So the resolution and frequency space, yeah, okay. So why is it that the asteroseismic detection informs us about the transit light curve? The reason is the following. It's sort of an intuitive piece of, a counterintuitive piece of physics, but it ends up helping us immeasurably in terms of constraining the planet for the following reason. It has to do with Newton's version of Kepler's third law, which looks like an old friend to all physicists. For folks who study binary stars, both of the masses and the denominator matter. But for people who study planets, especially people who study terrestrial planets like me, this is such a small term. So now you basically have the period of the planet, the semi-major axis of the planet removed from the star, and the mass of the star. And here's where the only piece of trickery comes in. You multiply the top and bottom by the radius of the star cubed, and you get this relationship where you have the period of the planet, which is measured so precisely for transiting planets, and you've measured the bulk property of the star with this other term, the semi-major axis divided by the radius of the star squared, which is a transit observable for reasons I'll tell you about. So, like I said, measured with very high precision for transits. So I've shown now a top-down view of a transit. You can see the semi-major axis span there. And based on the distance that the planet traverses in an entire orbit, this is 2 pi times that semi-major axis. But the fraction spent in transit is the fraction of time that the planet is silhouetted across the face of the star and is related to the number of radii that the star spans in that part of the radius. So basically, from the ratio of the transit duration to the total period alone, you get a constraint on the stellar density. So this is something which is like a piece of magic from Transiting Planets, which was first published in 2003, a year after the first transiting planet was found. But the reverse is also true. If you have a prior on the stellar density, and you know the period of the planet, then any of these things that are degenerate with the transit light curve fit can be affected with your knowledge about the stellar density. So what I'm showing here is, this complicated posterior distribution fitting of the transit light curve. There's a lot of terms in here. I've shown the transit up there. What I want to draw your attention to is the following. From the transit light curve alone, we sort of know the stellar density, so I've shown that A on our star at the bottom. So in addition to probing the stellar density, it's physically the units of stellar radii that the planet is removed away from the star. So it could be, based on the transit light curve alone, it could be 12 stellar radii away, it could be 9 stellar radii away. This translates in density to being between like 1.4 and 1.7 grams per cubic centimeter.
I don't understand how you get that without knowing where across the star it's...
There's some degeneracy, right. There's some degeneracy with the impact parameter. Yes, and so, what's that?
Just if you're bound on it.
Yeah, right. So if you know the transit, we know the transit duration to like 2 minutes. So it can either be perfectly crossing the largest chord of the star, or it can be down almost half as much. And that gives you, because the transit light curve alone, we've only constrained the duration, like I said, to like plus or minus a minute on either side. So that gives you this degeneracy, which is totally removed when you put in the asteroseismic prior. OK, so after imposing this asteroseismic prior, I've shown the density of the star here at the bottom, and anything, like I said, between like 1.7 grams per cubic centimeter cubed and like 1.4 grams per centimeter cubed is allowed from the transit light curve. But from this asteroseismic analysis, we know the density of the star is 1.65 grams per cubic centimeter plus or minus a milligram per cubic centimeter. And we can use this to constrain the rest of our curves in this, by applying this Bayesian prior and know that this star is very, very well constrained to be 12.2 plus or minus 0.1 stellar radii away from the star. And that removes all of this degeneracy, like you mentioned, with the impact parameter and so on. And it removes this degeneracy too, because it removes the degeneracy with impact parameter and the part of the star that the planet is actually grazing over. It removes basically any uncertainty in the transit light curve about the depth of the transit, about the duration of the transit, all of the things these things we've measured so well because of this prior of what we already know about the star. And so we can bring to fruition the promise of asteroseismology being measured to plus or minus 1% by knowing that we've measured the planet to plus or minus 1%, the dominant form of error on the radius of the planet.
How do you deal with the eccentricity degeneracy?
We argue that the eccentricity is 0 based on the following. First of all, the star is 6 gigayears old. And second of all, the planet has a period of 4 days. So we think, based on any reasonable understanding of tidal circularization time, there's just no way the planet could continue to be eccentric on that time scale. OK. That's a great question.
No other planets, so this is one star with one planet, or then
it probably has another planet, which I can tell you about, but I think it's much too far away for any residual eccentricity pumping to occur. A 1% error on a planet the size of the Earth is about 74 miles. So this is the planet for which we've measured it more precisely than any planet was measured in the 16th century, certainly. Now it's more precisely known than any planet outside of the solar system. So I was looking up sort of the history of measuring even the circumference of the Earth. I mean, this planet is 300 light years away, and we know its extent, to the distance I can see when I walk outside the University of Washington and I see Mount Rainier in the distance. That's 74 miles. We're starting to get to the realm where terrestrial planets are oblate. The Earth itself is thicker by about 20 miles along the equator than it is at the poles. And so I was looking up sort of what is the history of measuring the size of the Earth, and Wikipedia had all this information about what had been done in the 16th century. The truth is that the Earth itself was measured in about 1000 AD by a Persian scholar named Al-Biruni. And I'm showing here sort of an excerpt from his main scientific masterwork called Al-Qanun al-Masudi. Actually, the part of the book where he talks about measuring the circumference of the Earth from going to a tall mountain and looking down at the sea, and then going to the base of the mountain and looking at the sea, was just boring text. Boring. It's so I selected this image, but this has enormous historical precedent measuring the extent of a body, and this is the first time we've measured something outside of the solar system with a similar level of knowledge than we once did in the ancient world. And so now I'll sort of get to the piece of the puzzle that we know. How did we detect the mass of this planet? So now I'm sort of asserting we know the radius of this planet so well. The extent of the atmosphere of the Earth, depending on how you define extent of atmosphere, as it becomes so ethereal as you get up there, is about 100 kilometers. We're very close to measuring planets so well. But what is the mass of this planet? And we went to gather radial velocities. So I want to define radial velocity first. So the transit method is not the only way that we can detect extrasolar planets. In fact, as planets traverse their orbits around their star, just as the star is tugging on the planet is tugging on the star. And we observe the spectrum of the star to shift, sometimes by meters per second, which I think is truly remarkable. The state of the art of radial velocity characterization of stars is the speed of a person walking. For comparison, the radial reflex motion induced on the sun by the Earth is 10 centimeters per second. But we're so close. We're within, a factor of 10 of being able to do that.
Those lines that you observe.
Oh yeah, absorption lines.
Are broadened a lot because the star is hot, right? So
it depends on the type of star. Yeah, so the radial velocity method works much better for stars which are rotating slowly. It works much better for stars which are inactive. So meter per second is really the state of the art for inactive stars rotating very slowly. But you're right, there's pressure broadening, there's granulation at the surface of the star, and this sort of defines, this is a limiting factor in the precision that's possible for radial velocity measurements because stars aren't static.
But a relevant comment to that is that
Yeah.
in fact these measurements of the radial velocity are more precise than the width of any one line. Because they have many lines at high signal speeds
Yeah.
that they can measure, but the velocity is more precisely than the width of any line.
Yeah. So when we look at the radial velocity measurements of this star, we see the following. You can see that we're definitely detecting something. So this is a period of time. Kepler was launched in March of 2009. We detected KOI 69, the planet I'm telling you about, almost immediately after launch because the signal it presents is so pronounced in the light curve. And we observe this planet for, you can see gaps in time where the Kepler field is not visible from the Earth. It's on the other side of the sun, just to orient those who aren't observers. That accounts for the gaps in the data. You can see that something is tugging on the star, but it certainly doesn't have the period of the planet. So there actually is a detection of an Earth-sized transiting planet hidden in this data, but the overwhelming effect actually isn't that particular timescale. It's something tugging on the star with a period of 10 meters per second per year. So the immediate concern here, this is how I leverage the transit light curve to demonstrate that the planet is transiting the star we think it's transiting, which is this bright star presenting the asteroseismic signal.
So are you talking about the short period of sine wave, or are you talking about the general slope of that curve?
So there's two bodies that are imprinted in this radial velocity signature. There's one thing that is presenting a sine wave of amplitude 1 meter per second, which has a period of 4 days. On top of that is imprinted a much larger sine wave corresponding to a larger body located further away. And these things are combined to produce the radial velocity plot that I've shown.
Are any of those waves appear on the figure? You're talking about a sine wave.
I am, yeah. So
I don't understand the connection with
oh, okay.
the picture. I see wiggles on the picture, but
yes.
I don't know what that refers to.
The wiggles on the picture are meant to suggest the Doppler motion induced by the planet at a period of 4 days. So that's the short period on top. So I've actually stretched it out because it would be impossible to see. But then on top of that, so there's a component of the radial velocity that's this very short period sinusoid with period 4 days. And then there's this much longer component that hasn't turned over yet.
Okay, so the blue arrow thing
is suggestive of something else.
Sine wave.
Yeah, so something else is tugging on it. So we know about the planet tugging on it with a period of 4 days. Something else is tugging on it.
So this is not real data, this is a sketch.
This is real data.
But there are clearly not 90 periods in a year.
Right, oh, I'm sorry, yes. By sketch, you mean the squiggle that I put on top of the plot?
I mean, that sine wave curve does not have a period of 4 days.
Yes, so if I had put, you're right, it's meant to be suggestive. So if I had put kind of a sine wave with a period of 4 days, it would be indistinguishable from sort of a line. So I was meant to be suggestive, kind of with the squiggle, but you're right. And so there's something extra tugging on this planet in addition to that period of 4 days, that terrestrial planet. So the first scenario, of course, all we know is based on 10 meters per second per year. The sine curve hasn't turned over yet. It's bigger than 2 times the mass of Jupiter, and it has a period greater than 3 years. The optimal scenario for me, an exoplanet scientist, is this is probably another planet. That's very interesting, given the fact that this planet, KY69, couldn't possibly have formed in situ, so close where it is, completely roasted. There's obviously a rich dynamical history related to this architecture. We have one planet very close in.
Why do you say greater than 3 years? It looks like it must be greater than 10 years or something. It hasn't been...
That's a lower limit. Yeah. Yeah, you're right. The other scenario is that this isn't another planet at all, but another self-luminous object. The reason why this would be worrisome is because then maybe, perhaps, the planet isn't transiting the star we think it's transiting, this bright star that produced the asteroseismic signal. It certainly is suggestive that the density of the star that we infer from the transit light curve matches that from asteroseismology. And indeed, I can leverage that to demonstrate that it's not transiting this other thing, this other putative small star which is producing this large radial velocity signature.
How do you know that that's not just because the star is moving towards or
You mean why it's not kind of like drifting in space?
Sorry, the big blue line.
Uh-huh.
Have you resolved it turning over?
No, we haven't.
So if it's just a line, then it could just be moving towards us or away from us.
It's variable acceleration. This is a change. The slope is acceleration.
Oh, sorry.
Yeah.
But the equivalent question would be, are there just gradients in the potential in the galaxy such that that could just be the local acceleration, or is the amplitude of that acceleration much too large?
I think the amplitude of the acceleration is too large.
I think so too.
Yeah. So basically the reason why I talked about validating this planet, concluding that it's transiting the large solar-type planet which presents these asteroseismic signatures, is because the density of any star that the planet is transiting, it's possible to dilute the transit signal by throwing in extra stars within the center where we're measuring the light, but you can't mimic a transit duration. You know, the transit duration is telling us crucial information about the density of the star. That star has to be larger, based on our knowledge about stellar evolution. It has to be larger than about 0.8 times the mass of the sun. And we would have seen such a thing in the adaptive optics imaging. This star is so bright, it's so close, that it's about 300 light years away. So it's easy to resolve distances down to 20 AUs. This is all adaptive optics imaging gathered from the Keck telescope in Hawaii. And so for this reason, I sort of concluded, I argued, that the planet is transiting, that the planet is transiting the star we think it's transiting. It's a separate piece of evidence that the star itself, the bright star, is exhibiting this motion, every 4.5 days, which is really the smoking gun that the planet is going around it. But this is kind of a second piece of reasoning that I thought was a lot of fun. So in this really largely unpopulated part of parameter space, there now exists something, KOI 69, and it's not the only one, but it certainly is the best measured. So here's our knowledge about this part of parameter space. And it's sort of, very suggestive what the composition of this planet is. It's going right through this part of parameter space that's suggestive of rock, but indeed there's a lot of variability here. This is something very strange. And I'm only showing 1 sigma error ellipses. The 2 sigma error ellipse for this planet actually passes through a part of parameter space which is less dense than water. There's a 3.5% chance that the planet actually has some large gaseous atmosphere piled on top of it. And there's another chance that this planet is almost as dense as iron. And this is with me marshaling just all of the resources that are available to the exoplanet community, which is why I say this is a laboratory. These planets are very unstudied because there's none in our backyard. And you can see that, they vary, even in this part of parameter space, which is incredibly underpopulated.
But couldn't you just argue that it's very unlikely that it has an atmosphere, given that it's so close to the host star?
Yes, you could. Oh, yeah, you could. So if it did have any water, it probably would have outgassed, especially over 6 gigayears. Yeah, but then how do you explain? It's difficult to explain, Kepler 11b, which is very close into its host star indeed. So there's something which is very odd about that. I mean, you have to have you can have an atmosphere of perhaps very high mean molecular weight, but a very puffy atmosphere would be very difficult to describe. I think I'll go ahead and skip this slide. I've gotten lots of.
Can you have transient atmospheres like you had among solar system objects?
Can you have what? Transient atmosphere.
Like
You could. You could, but I think for such a transient atmosphere to still reside 6 gigayears later is unlikely. Yeah, but perhaps when the star first formed. So I want to conclude in my last final minutes with a statement about sort of the future of the study of exoplanets. So I sort of already mentioned the Kepler Space Telescope is hobbled. This is a singular instrument which really revolutionized the face of exoplanetary astronomy. The next thing in line, it sort of speaks to the promise of exoplanets, is the fact that NASA selected another exoplanet search mission to be launched so soon after Kepler, which is the TESS mission. So this was actually just announced that NASA was going to fly it in April of this year. And I was at a Harvard alumni reunion event with exoplanet people, and people were crying. They were so excited that TESS was going to be launched, because while Kepler looked at a single patch of the sky, most of these are hundreds if not thousands of light years away, the TESS mission is looking only nearby. And it's making use of the riches, the statistical riches that Kepler dumped in our lap about planet occurrence rates. And so now we know, just from the TESS mission looking at nearby planets, we'll find dozens of Earth-sized planets, a handful of which will be in their habitable zone. So this is something which is coming up sort of very soon. But in the meantime, Kepler is hobbled, TESS hasn't launched yet, and I want to remember an old friend to me, which is the Spitzer Space Telescope. Spitzer Cycle 10 proposals were due really recently, and every astronomer I knew was thinking, every exoplaneteer I knew was thinking about how to leverage Spitzer in this time when there's nothing in space to study exoplanets anymore. And we came up with a couple of ideas. The first was following up on transiting planets whose transits don't appear in a regular periodic fashion because they're being tugged by other planets. You know, that data, that planet has stopped speaking to us through Kepler, but we can still follow up on it with Spitzer. And a proposal, you know, that we wrote, which is very risky but very high reward, is to actually leverage Spitzer as a survey instrument, you know, especially around the smallest stars. You know, so for sun-like stars, in order to get small planets in their habitable zone, you have to have incredible photometric precision and you have to stare for months and months of time. But around the smallest stars, transit signatures of Earth-sized planets are proportionally much larger because you're blocking a much larger fraction surface of the star. And their habitable zone is so close in. You could look at only 30 perhaps and see one. And we now know that planets are so common around M stars. And so these are sort of mock-ups of nearby M stars where we could very easily see things half the size of the Earth or the size of the Earth. So this is a very risky proposal, but it's something Spitzer's capable of doing, and it sort of enables me to close the study with why KOI 69 is so promising to me. And this is sort of a story where when I was writing the slide, I was thinking about being a graduate student and wondering if you were going to contribute something meaningful, you know, in the tenure of your graduate career. At the time I was working on Spitzer data, I was thinking about how I could possibly improve on the systematics presented by Spitzer. And this was something I was working on, you know, wondering if what I was working on was worthwhile, was having any echoes in the community. This was something, you know, I was a pie-in-the-sky idea. I was using Spitzer to search for planets, extra planets around a system for which we now know there are no extra planets. And the main sort of sensitivity problem with Spitzer is that it executes this pointing jitter. What I'm showing here is the sensitivity even over a single pixel. You know, so this tiny signature you're looking for of a transit is totally blended in with the spacecraft's pointing, sampling higher and lower portions of the same pixel. But the Spitzer Space Center took off with this idea. You know, and they started dragging a single star all over portions of the pixel to make a pixel flat field. So that
Stochastic jitter, or it's
no, it's driven by a battery heater cycle on board Spitzer. It executes an ellipse. 30 minutes. It used to be an hour until exoplanet scientists argued that we had to decouple the time scale of that battery heater from the time scale of a transit. So it's no longer an hour, it's 30 minutes. And they picked up on this and mapped the entire pixel. You know, and it's not only this particular pixel mapping that improves the quality of Spitzer, it's the so-called method called peak up, and by which they use an additional reference star within a certain brightness range. This was an idea that I, as a graduate student, got to contribute to. It was I who suggested, why not try KOI 69? Not knowing at the time that it would be so interesting, that a mass measurement would be possible, that asteroseismology would be possible. And so the Spitzer Space Center took off, you know, from the two transits that we gathered of this planet. David Charbonneau was my advisor, and this was his guaranteed observation program, and booked another 5 measurements of this particular transit, 2 of which were using this special, 2 of which weren't using this new special method by which they not only have the pixel mapped, they point the telescope at the part of the pixel for which the gradient is smallest, which is to say where the peak sensitivity resides. And they point up to it again and again. And did this experiment, you know, 2 visits without peak up and 3 visits with. They're overplotted as sort of the sensitivity so that you can see. And I just, you know, I have 1 more minute. So I want to conclude with the fact that we only meaningfully detected the transit of KOI 69. You know, there's no way that the Spitzer Science Center would have spent so much time looking at a planet whose transit could maybe be detected by 1 sigma unless they were trying out this new observing mode, which it turned out multiplied our constraint of the planet's transit depth by a factor of 2. You know, what I'm showing here is the posterior distribution, including the effects of systematic noise of the transit depth. You know, so here's a flat line, and here's the depth that we'd expect from Kepler. You know, and I know that this doesn't look very impressive, but a factor of 2 is a huge deal in the exoplanet community when there's no Kepler and we're still waiting for TESS. And so I'll sort of conclude by reiterating again the sort of strangeness of the universe where there's so many super-Earths. You know, I want to re-emphasize this part of parameter space, that the laboratory experiments taking place to understand worlds outside of our own solar system aren't only high pressurized environments with magnesium silicate. The Alien Earth Initiative, which has just been approved for money from the Templeton Foundation, this is a collaboration between the Smithsonian, Harvard, and MIT, uses labs at MIT that are devoted to observing animals and how they produce biosignatures, and also cloud chamber experiments to better characterize atmospheres in high gravitational environments. So this is sort of a period in exoplanet science where laboratories are not only other worlds, but it's our own laboratories on Earth that are informing our understanding of these really strange places in the universe. And I'll sort of conclude with big questions of habitability. The reason why we're spending so much time characterizing individual worlds is because when JWST flies, when the James Webb Space Telescope flies, we'll probably get, we, the exoplanet community, are going to get enough time to maybe characterize one atmosphere, and we want to get it right. Is it possible that something 2 times the radius of the Earth is habitable? We want to answer those questions now. And where is that planet so we can look at it? This is something which might be discovered with TESS, but maybe even sooner with Spitzer. So thank you very much for your time.
Time for questions?
So this JWST
Yes.
is an infrared telescope.
Yes.
So how using this infrared telescope you tell us something about the atmosphere?
For the following reason. So the best way, there's 2 ways that you can really measure the atmosphere of an exoplanet. The first is if you can resolve the exoplanet different from the star and simply lay down a slit on top of the planet and measure its atmosphere. This is something which is a basically impossible proposition because stars are so much brighter than planets and because planets are so close into their stars. Maybe with a coronagraph, a flying coronagraph located in AU from JWST. And this is something which, the coronagraph has actually started being built at Princeton. This is not like a pie-in-the-sky idea. That's one way. The other way is that you wait for the planet to transit. So you need a transiting planet. And then it's not only the solid, optically thick part of the planet that passes in front of the star, the atmosphere also passes in front of the star. And the atmosphere preferentially allows some photons through for where the atmosphere is clear and blocks those for which the atmosphere is not clear. And so imprinted on if you observe the transit at different wavelengths, the planet will actually appear larger, because its atmosphere is actually thick, or its atmosphere is opaque at wavelengths where you have particular particulates, or molecules that are thick at that wavelength. So the reason why you measure those in the infrared is because biosignatures are in the infrared. So if you look at infrared signatures of the Earth and Mars and Venus, you can see CO2, but it's only on the Earth that you see ozone. And this is something which life produces. There are many things that are abiotic, but you really need to look into the infrared to see these things which would indicate life as we know it.
But the dwarf planets, are those cool enough that the habitable zone would be closer in and therefore it's easier to see them if you're already transit because the period is shorter?
With dwarf stars or dwarf?
Dwarf stars, sorry. Dwarf
yes.
Stars.
No, exactly. So that's where we want to look. I actually have a slide.
Them being much cooler.
Yeah. So it's not only, there's so many advantages to looking around cool stars. The first is that any signature presented by the planet is larger. So the planet blocks fractionally more area. When you look at with radial velocities, the star is less massive, so a bigger reflex motion is induced by the same size planet. They're more numerous. They host more planets. These are things which are also true. And then what was the final thing I was going to say? Oh, and the periods are shorter, right. So the habitable zone is located in much closer. You see more transits, and the transits are more likely to occur, because when the planet is closer in, then it's much more likely to transit. So for all of these reasons. So this is sort of the TESS mission and what it will look for. And you can see that it's not actually looking only for M stars, but the Kepler mission roughly stopped at like 0.8 times the mass of the sun. There's some things down here. A ground-based mission called the MIRF looks smaller than this, and the mission that I talked for, the project that I proposed for with Spitzer would look at the very, very smallest things. But it's going to study stars in this region, and it's going to be the vast majority of the Earths that it finds will be in that part of space. You can sort of see the number of Earths that TESS anticipates to discover is very large around the small stars, and it's precisely because they're easier to see.
So, last question. So
Yeah.
in terms of the
Oh yeah.
So the idea also why a lot of professional astronomers look at it is to see that if you could study the atmosphere
Oh yes.
of Venus
Yeah.
using this very nearby light stream to see if we
Yeah.
can actually detect anything
Yeah.
when we do it actually with exosolar planets.
Yeah.
So do you know what were the results? Could they really?
Those are, I don't think they're published yet. There's two surveys which were done. So how on earth do you point the Hubble Space Telescope at the sun to study the transit of Venus? I mean, you would just burn it, like looking into the eye of Sauron or something. The answer is there was two answers. One group actually looked at the sun, looked at the surface of the moon. You know, so you're actually looking at specular reflection of the sun's light off the moon, and then you can resolve the transit of Venus. Another group did reflection off one of the planets. I forget which one. But they actually just observed the planet, and then the fraction of the star's light that was reflected off of the sun's light, which was reflected off the planet, you could see a decrement corresponding to the disappearance of Venus. So, you know, it was basically the only way. I don't think either of those results have been published.
Could they get atmospheric information?
Yeah, exactly. I mean, that's the idea. They did? I mean, that's the answer? I don't. I don't think it's been published, is the answer.
The data are probably public, so we could just grab them.
The data are probably public.
We can cancel dinner and just grab them.
So what you're saying is you can get the information about the atmosphere of Venus by looking at the light from the sun bouncing off some other planet?
Yeah, especially if you look at the moon, because if you're assuming that, I mean, you have to make the assumption that whatever you're looking at isn't going to preferentially absorb or reflect light. You know, hopefully it's going to reflect all wavelengths the same, which a gray or, you know, white surface usually does. So what you're hoping for is that you can look at the moon at different wavelengths, and the reflected sunlight that you see, you'll see a different depth of the transit of Venus. Yeah, I actually don't know if that, the proposals were approved.
On that note, let's thank Sarah again.
Thank you.